Welcome back. We'll continue with the discussion on filters. Let's start. In the previous session, we saw example of a low pass, high pass, band stop, band pass, and band reject filters, right? Then in the last session, we concluded that this is very difficult to realize this filter in practice. Means we cannot have this practically, right? This is very difficult to realize this filter in practice because we cannot make the frequency response to go from 1 to 0 directly at a given frequency. Means at a single frequency we cannot make it to go to 0. Instead, what we can have, we can make this filter to go to 0 a rule of like this. We can do this, but we cannot do this. This is very difficult to build this system or filter practically. And instead we can have a steady roll of this filter, means to go from 1 to 0 steadily, and this will do this at some rate. For example, you might have this seen in control theory that we say that this magnitude decreases at some dB rate, right? For example, minus 20 dB per decade. It does it something like this. One more thing, we allow the response of this filter, means either in pass band is flat. You can see the response of this is flat, and there is same way in the high pass filter. If I say the filter is high pass, is a high pass, we say that in this the response is again flat, right? Means we do not allow any kind of decrease in the amplitude of this in either pass band or stop band, right? Now practically we do allow some ripples in either pass band or stop band. We do allow it, right? And that will give us different type of filter that we shall learn in a bit. So we may allow the filter to do something like this in either pass band or in stop band, like this for a low pass filter. We can allow it to do this. All right, and we allow and based on this, whether we allow this in pass band or stop band, based on this we have different type of filters that we'll name in a bit. But and for a practical filter which does like something like this, please remember this, for a practical filter which actually rolls off like this, the cutoff frequency is defined like this. Please remember this. Cutoff frequency, if the magnitude here is A, suppose if the magnitude of this is A, and when the magnitude of this drops to 70%, then that frequency is referred as the cutoff frequency for a practical filter. So we say this is the cutoff frequency, right? So this is the frequency at which the magnitude drops to the 70%, which is the magnitude at 0 frequency for this. Same way, if I say this is a high pass filter, so if the magnitude here is A, sorry, so if the magnitude here is A, then the frequency at which the magnitude rises to the 70%, then that is referred as cutoff frequency. All right, and the region between this frequency and this frequency, let's say this is the pass band edge and this is the, sorry, let me use the, I'm using omega, capital omega c here, so this is omega c, sorry, not omega c, this is omega p. So let me call this edge as omega p, this is omega c, and this is omega s, right? So this is the point where the response, and this is the frequency at which the magnitude is still A, sorry, yes, on A, and this is the point where we have some magnitude omega s, and this is the beginning of this stop band, and the region between this omega p and omega s is referred as transition band. This is referred as transition band, and transition band is the band where actually the roll-off starts from pass band to stop band, or from stop band to pass band in high pass filter, right? So this is the band where the actual roll off stops. So for a high pass filter, you can say this is the transition band. So you can say this is the transition band. Same way you can define these quantities for this band stop and band pass filters, right? So one more thing, we can allow the, see here the response remains constant in the pass band. In the stop band, the response again remains constant, but we can allow the some this we can allow practical filters to have some ripples like this, or in stop band we can allow it to flow like this. Then you see this is the roll off from pass band to stop. So this is our stop band. This is pass band, this is stop band, and this is referred as transition. So this is our transition band, and you know this is the cutoff frequency. This is omega p, this is omega s, right? So between omega s and omega p, we have transition band. And based on this, whether we allow the frequency response to remain flat in pass band, stop band, or allow some ripples in pass band and stop band, we have different type of filters, and these are first type is Butterworth filter. Second type is Chebyshev type 1 filter. This is referred as Chebyshev type 1 filter. Third type is Chebyshev type second filters. Fourth type is elliptic filters. And fifth type is Bessel filters. Bessel filters. All right. So these are the different filters that we get, whether we allow the ripple to be present in pass band, stop band, or whether the response of the filter remains flat in pass band and stop band. All right. So what's a Butterworth filter? Now Butterworth filter can be low pass, high pass, band pass, stop, and there's band stop filter. Okay. So you can characterize the Butterworth filter as low pass, high pass, band stop, band pass filters, right? So first let us see the now Butterworth low pass filter. Let me show you the Butterworth low pass filter. So Butterworth low pass filter frequency response. Now this filter allows the frequency response to be flat in both pass band and stop band. So this is a filter which has a frequency response like, again this is a practical filter. So now this the frequency response remains flat in both in pass band and in stop band and in stop band. So the frequency response of this filter which of omega is flat both in pass and stop band, and we say this is omega c means the cutoff frequency. This is omega s and this is omega p. Sorry, this is omega p and this is omega s. All right. So this is a Butterworth low pass filter. Same way you can draw a Butterworth high pass filter, right? So that's a filter which has again which allows this which allows the filter response to be flat in both the bands, known as in pass band as well as in stop band, right? Now the transfer function, I will give you the transfer function of this means h of omega, or you can write h of s also. You can write it as h of also. Simply replace omega by this. Now the transfer function square, magnitude square of that, you can write it like this. This is the transfer function of a low pass filter, low pass Butterworth filter. This is the transfer function of a low pass Butterworth filter. Please check it again. I think it's correct. All right. So this will give you this characteristic. This will give you this. What is omega c? Omega c is a cutoff frequency. What is this m? N is referred as the order of this filter. Order of filter. So N is referred as order of the filter. Now let me first give you the transfer function in S domain also. Now the transfer function in S domain looks like this, so that you are not confused. So simply what we have done, we have replaced S by omega, right? So this is a transfer function in S domain. Now N is the order. As you increase the order, the transition has become sharper. So this will you have, if the order is low, you will have some characteristics like this, means if the N is low. Now as the value of N increases, the characteristics will go sharper and sharper. Means it will go like this. Sorry, this should do like this. So the character means the transition band becomes smaller and smaller. So as the order of the filter goes up, the transition band decreases. Transition band width actually decreases. Remember that. Okay, so this is a Butterworth low pass filter. Now the Chebyshev type 1 filter. Chebyshev type 1 filter. Now the frequency response of this filter allows uh, this filter allows a ripple in the pass band, this pass band. Or if I say low pass filter, Chebyshev low pass filter, you will see the characteristics look like this. The rule of starts here. So this filter allows a ripple in the passband. If I say this is 1, then this will be 1 minus delta P, right? So delta P means the decrease. This allows the magnitude to vary from 1 to 1 minus delta in the passband. So this filter allows the frequency response to vary between 1 and 1 minus delta P, means it allows a small variation in the passband, and the stop band is flat. Stop band is flat. Now, why do we want to have a ripple in this? Why do we, if the frequency response is flat, wouldn't it be better? Because this won't allow any distortion in the output then, if the frequency response looks like this. Why do we allow it? Because if we allow the frequency response to be flat in both the bands, the order of the filter will go very high. The order of the filter of will go very high. Although this is very important for applications, especially in communication. But if we can allow this ripple, means if we can allow this ripple in our application, means if we are okay with this ripple that is present in the pass band, then we can decrease the this order of the filter very much. All right, and we will have a sharp cutoff for the same order of the filters that for the Chebyshev type 1 and Chebyshev, and Butterworth filter. So first thing is, why do we allow the this ripple in passband? Now, if we can allow it, so the order of the filter will decrease. Order will be small compared to the Butterworth filter, compared to the order that we'll have in the Butterworth filter. So as you can see, as the order increases. Now, what do we mean by order, by the way? You might have studied analog filters already. Order simply means the number of components, how many R and C components. If you design a filter, low pass filter by R and C, resistors and capacitors, the number of components you have to increase. That's the meaning of literal meaning of order here. All right. I hope you got the idea. Same way, now if we allow this ripple to be present in the passband, the order will be smaller compared to the Butterworth filter. Now in Chebyshev type 2 filter, this filter allows the ripple in stop band, means the frequency response is flat in passband, but in stop band it allows this. So we have a ripple present, and how much is the ripple, means how much magnitude we allow in stop band. Let's call it delta. Otherwise it should have been 0, means that omega s we allow a magnitude of this which is equal to delta S, and it's flat in pass band, and the pass band response is flat. So this is Chebyshev type 2. In elliptic filters, next type is elliptic filters. So this filter is the one which allows the ripples to be present in both pass band as well as stop band. So this is a filter which has ripples in the pass as well as in stop band. So this has so the magnitude here varies from 1 to delta 1 to 1 minus delta p, and here we allow non-zero value of this h of omega of delta. Right? Now, what's the benefit of allowing the ripples in both the bands? The transition band is the roll off, and the transition band is the smallest. So the transition band is smallest in elliptical filter, smallest transition band. So this filter has the smallest transition band. For the same order of the filters, to compare the same order, means for the Butterworth, Chebyshev type 1, Chebyshev type 2 are elliptic filters, the order will be smaller in this. To have some filter characteristics, the order will be small in this. mm, Sorry, not the order, the transition band will be smallest in elliptic filters. Now the last type is the Bessel filters. Last type is the Bessel filter. Last type is the Bessel filter. Now this has a maximal flat response in both the bands, one is in pass band and in stop band. Now, if you see, the Butterworth filter has the identical response. Only difference is this has larger transition band as compared to this Butterworth filter. So the transition band of Bessel filter is greater than that of Butterworth Butterworth filter. So the transition band is larger than. Now, what is the advantage of having larger transition band? The filter has linear phase. This is very, very important. The filter allows linear phase. So Bessel filter has linear phase. Means this allows a linear phase. Now, what do you mean by linear phase? Means the frequent phase of this system or the filter is a linear function of omega. Right? It varies linear. All right, and if it's minus k times omega, this will correspond to simply a delay of the signal without any distortion. So this will allow a delay of the signal without any distortion. For example, if I say input to the system is this, so this is the input to the system. The output, what will happen if you pass it through a Bessel filter? This simply means this will be delayed by some amount, but without any distortion. So you can see, let me try it on the same scale. Let me draw it on the same scale. So if this is the input to the system, so suppose these two pulses are input to the system, the output will be simply delayed. Means the output will be simply delayed, but the same output will be identical. Only difference is it will be delayed. So this is the advantage of, sorry, different amplitudes, but the amplitudes, but the So what is this system doing to the input? It is simply delaying it without any distortion. This is very important for applications in communication, especially in speech processing or this music signals. All right. So these are the different type of filters. Now I have shown you only the low pass version of all these. You can have high pass, you can have band pass, you can have band stop type of these filters. All right. So I have given you only the low pass. So how do we differentiate these filters? Based on whether the ripple is present in pass band, stop band, and how much we have the transition band, right? That will decide the type of the filter, and accordingly that you can use the filter for a particular application. I hope you have got the idea. In the next session, we'll see these filters in the MATLAB, right? We'll see a little bit about these in MATLAB, all right? Okay, let me end this session here.